overall feel of it, it was good. All right, what's the next one? So what information did I give you on this one? Did anyone do this one yet? X squared plus y squared less than or equal to 1? Yes? Z equals 0? All right, so there are two different surfaces here. We have the bottom of this thing, right? The bottom of this, which is very much like the side of that one we just did, except now this one's in the xy plane. So if we call this bottom surface S1, that'll be our first surface, R1 of u, v, which will be v cosine u, 0, v cosine u, v sine u, 0. U between 0 and 2 pi, v between 0 and 1. So that should draw us the disk that's on the ground, right? And then for S2, which will be this top part, the only difference between S2 and S1, if you look at them from the top, they're identical, right? The only difference is that z coordinate, or z component function, needs to be controlled by that paraboloid looking thing, right? Right, this piece. So we have my second surface of u and v will have the same exact x and y components, but my z now should be what?
It should be the other equation.
Yeah, it should be this, right? So when I plug that in, I should get 1 minus v squared. Because your cosine squared u and your sine squared u, right? This will be v squared cosine squared u minus v squared sine squared u, and then you can factor out the v squared and you'll get a 1 there. So, and then same restrictions, right? Same restrictions. Any questions on that one? Sure? All right, the last example, I think I'll leave that one to you. I think this one is within reason for you to do on your own. No bonus or anything, just you do it on your own. You don't need to turn it in or anything. And just so you have the answers, I'll just show them on the board. That way you can see what they are. Where are they? So if you want to go back and look at this, you can. One of them is this one, u, v, 1 minus u squared with u between negative 1 and 1. And then v is between 0 and 2 minus 1 plus u squared. I guess that could be 1 plus u squared. The next one is this one right here, u0v, u between negative 1 and 1, v between 0 and 1 minus u squared. And then the last one is u, 2 minus v and v, u between negative 1 and 1, v between 0 and 1 minus u squared. So those are the three parametric surfaces. All right, I hope that exercise helped at least get a feel for how we draw these things, right? Because now in the next section, like I said, we're going to assume now that if someone gives you a surface, you can come up with a parametric representation for it. And now we're going to do some more calculus stuff. Surface integrals. Given a scalar function f on a surface S, that surface S is given with the vector equation r of u v. Then this right here, this notation, is the new notation for this section, at least the first formula for this section, which is called the surface integral of f over s. So the best way I think I can explain this is that this right here is, you have some surface out there, right? You have some surface? And what we're saying is, if you were to go to each point on that surface and take the value of a function there. So think about temperature. We've done this already. You know, imagine you have a surface and you were to take the temperature at each point. Then what this integral does is it adds up the temperatures at every single point. You could also think of this as like if you had a surface and you had density at each point. Then this would add up all of your density times area, which would give you like a mass. So the difference between this and the previous sections is that we did something like this along a curve. Now we're going to move along a surface. Right, so what is the computation we do for this? You should recognize that. What's that right there? If this is a 1, then what is this? This is the surface area, right? That's the area of the surface. But now what we're doing is we're multiplying it times some function evaluated along the surface. So we're somehow taking a quantity at each point and adding them up. So here's your first example. Find the double integral over s of xyz ds. So we've now seen a lot of this stuff change, right? We've seen like dx, cal2 dx, right? And then we went to like dA, dv, d little r with the vector on it. That was work integral. Now we're seeing d capital S. What was d little s? Do you remember when we saw d little s? Arc length. That was an arc length one. So all of this letter right here, this thing right here, totally changes what we're trying to do. In this case, capital S is with respect to surface area. All right, so we need to look at this cone here, right? We need to see if we can find a vector function that will draw that cone. So can we come up with a vector function that would draw that cone? So this is a special case because our cone equation is, that surface is a function of two variables, of x and y, right? Like you can look at the z-coordinate as a function of x and y. So our vector function can look like this. Square root of u squared plus y squared. See if you believe that. Do you believe that? Yeah, I don't know why I put y squared. I meant to say v squared, or I meant to write v squared, and I meant to say v squared. Okay? So u is u, v is v, and the z is a function of both u and v. Right? So the integral, I'll put it over here, when we're trying to do the double integral over s of some function of x, y, z, right? With respect to surface area, this is the double integral over s of our function evaluated along the surface, and then times the magnitude of the partial of r with respect to u crossed with the partial of r with respect to v d a. Sorry, this is over the domain D. So that's the note that I just had up right here. Okay, so the double integral over the surface S of the scalar function with respect to surface area is the double integral over D. Now D is the domain on U and V of the scalar function evaluated along the surface, and then that's your surface area formula from last time. So we just need to execute this formula now. Yes, so that was going to be my question to you is, can we use this? If this right here, right? If this right here, well, this whole thing, if this whole thing is this, right? Then can we use the shortcut? The answer is yes, and what I want to do is show you it both ways. So I'm going to do it without the shortcut first, then I'm going to do it with the shortcut, and I think you'll agree that with the shortcut is a little bit faster. Yeah, it is truly a shortcut, yes. All right, so let's keep going, all right? We're going to need some partials, right? So let's partial of r with respect to u should be what? 1, 0. So we're trying to take u squared plus v squared, all that raised to the 1/2, and take the derivative of it. So the 1/2 comes out, u squared plus v squared to the negative 1/2 times the derivative of what's inside with respect to u is 2u. The 2 and the half cancel, so I should just get u times this, right? Or u over this thing. So u over the square root of u squared plus v squared. Okay, that's our partial of r with respect to u. Partial of r with respect to v, 0, 1, right? And then this part will be identical to this part will be identical to this, except I'll have v up top. So v over square root of u squared plus v squared. What am I supposed to do with this? Cross them. Okay, so let's do the cross. So I cross this. And I'll do it over here. So r, partial of r with respect to u, cross partial of r with respect to v, should be another vector. All right, this should go pretty nice. Let's see. Cover that up. 0, right? And then minus this. So minus u over square root of u squared plus v squared. Okay, the next piece, I cover up the middle. I do that one, and then this one will go away, but then I have to make it negative. So negative of this. And then our last component, just 1. Right? And then we take the magnitude of this, which is going to be the square root of this squared, right? So u squared over u squared plus v squared, because I square the top and bottom. Then plus this one, which is v squared over u squared plus v squared, and then plus 1. And what is that equal to? They have the same denominator here, right? So add those together. You get u squared plus v squared over u squared plus v squared, which is 1 plus 1 is 2, root 2. Well, that's not so bad, right? Root 2. All right. So I have this part, right? This part is just root 2. And then I need to take my scalar function and evaluate it along the surface. So what is my scalar function? My scalar function evaluated along my surface. So what does this mean? Well, what is my scalar function? X, Y, Z, right? So this just means I'm going to take x times y times z, but I have to be looking at the x from this thing, the y from this thing, and the z from this thing, which I just erased.
Yeah.
Okay, so the x was what? U. The y was v, and then the z was square root of u squared plus v squared. So that's what this is, right? Okay, I think we're ready for the double integral then. So now, finally, the surface integral of x, y, z with respect to surface area should be the double integral over d of that u v square root of u squared v squared times the magnitude of the cross product of the partials, which we said was root 2, so I can bring that out here, and then dA, right? Now a little bit of a tricky part. We need to figure out what our restrictions on u and v are. So what are our restrictions on u and v that will draw this? So what are our restrictions on u and v that will draw this? So what are our restrictions on u and v that will draw this? So what are our restrictions on u and v that will draw this? So what are our restrictions on u and v that will draw this? So what are our restrictions on u and v that will draw this? So what are our restrictions on u and v that will draw this? So what are our restrictions on u and v that will draw this? So what are our restrictions on u and v that will draw this? So what are our restrictions on u and v that will draw this? So what are our restrictions on u and v that will draw this? So what are our restrictions on u and v that will draw this? So what are our restrictions on u and v that will draw this? So what are our restrictions on u and v that will draw this? So what are our restrictions on u and v that will draw this? So what are our restrictions on u and v that will draw this? So what are our restrictions on u and v that will draw this? So what are our restrictions on u and v that will draw this? So what are our restrictions on u and v that will draw this? So what are our restrictions on u and v that will draw this? So what are our restrictions on u and v that will draw this? So what are our restric
V be between 0 and 1?
Pardon?
Should V be between 0 and 1?
V be between
0.
0 and 1. Where are you getting that from?
So it's like you're looking at the cone. It starts at the origin, right?
Mm-hmm.
And it goes up and it meets the sphere down the very top, because the top is rounded, right? It's not flat, because it has to meet that sphere.
Yeah.
And the radius of the sphere is 1, so the highest it can be is 1.
Yes. I have a problem. I have a major problem. I actually misread this problem. Okay, so here's the way I just read it too fast. I'm treating my S as the cone. Do y'all see that? I'm treating my S as like this is my surface. This is my surface.
I really thought I was going crazy.
Yeah, were you?
Yeah.
Okay, good. I'm glad that you felt that way. Look, the way I read this, I'm treating my S as the cone itself.
Yeah, I was like,
Okay?
that's a weird.
And then where it hits the sphere is where I'm going to stop the cone. That's not the way the problem is worded.
Because it's above, the sphere itself is above the cone.
Yeah, the way this is talking about the surface is this top piece up here. That's what S should be.
Yeah. Yeah.
Do y'all see the difference between that?
Yes.
Now, can we still do it the way that I am working the problem?
No, you ruined it.
No.
What?
You're done. You're done.
No, I mean, we can. Look, I mean, did we come up with an R of UV that would draw the cone?
Yes. But the boundaries are going to be different, though. That's the problem.
Right? Now, will this draw the cone? Yes, but I still need to figure out what my U and my V have to be to draw the cone. Agreed?
Yeah.
Okay, so what I'm going to do, because I don't want to have to redo this whole thing, is I'm going to take out where S is, I'm going to say where S is the cone, okay? Where S is basically this cone, where it hits, and then you stop it where it hits the unit sphere. Okay, so I'm basically this black part, okay? Because if I read this problem correctly, which I didn't, and that's my fault and I apologize, then we should be using the first surface that we had when we started class with that sine U, cosine V, sine U, sine V, cosine U. We should be using that to draw this little piece of S as opposed to what I'm using, okay? I don't know, I didn't realize it until I got to this because I was like, okay, how are we going to define the domain of S? What are our restrictions on U and V? All right? So can you tell me how I can do this part? I'm trying to draw this cone, right? I'm looking at this surface S as a function of U and V, which are really like the X and Y on the ground, right? My U and my V are like on the ground. And then this cone is the,
But now we're only looking at the side?
we're only looking at what?
The side, the black part?
Yep. Yeah, not inside the cone, just the surface, right? So can you tell me how I'm going to draw that? Like, what are my restrictions on U and V? What is that on the ground? It's a circle, right? Which means you're going to have to go to what? Like this on the ground is not a nice Cartesian region. So you're going to have to go to polar. Okay? We're going to have to go to polar here.
We're going to have to find we're going to use like R and theta.
Sure, we'll use R and theta. So we'll go and we'll replace U with R cosine theta. We'll replace V with R sine theta. And then we'll have a good way of defining this. Yes? Okay, I'm just going to keep going because that's where we are. I mean, U is going to be R cosine theta. V is going to be r sine theta. Our restrictions on r and theta are going to be what?
The theta is going to be 2 pi.
0 to pi. And
R
then,
is going to be 0 to 1.
is it 0 to 1?
Yeah.
It's 0 to something, right? It's 0 to something, but is it 1?
No, it's less than
It's not 1, right? It's wherever this hits the sphere and drops straight down. That's our radius, right? So we have to figure out where it hits and drops down. It can't be 1 because it's a unit sphere, isn't it? And that would mean if it was 1, then it would take me all the way out to here, and that wouldn't be, right? Because the radius of the sphere is 1. So where do those hit?
I think it was right up over 2, because I think this is on one of the...
Yeah, this is on the mini exam, right? But let me run through how we're going to do it. So this is I mean, I totally dropped the ball on this. I should fail the class. But what I'm doing is still within what we can do. Like this is not complete. It's just a different surface, right? Okay. So I'm going to now try and figure out where the sphere and the cone hit each other so I can figure out the radius restrictions. So if we were to take a cross section of the unit sphere and then take a look at our cone in here like this, right? We're trying to figure out where that hits, right? So if I call this maybe U, and then this is like our Z, right? It's almost like what I'm doing is cutting this in half and taking a look at a cross section, right? So that would mean V is 0, right? If V is 0, I'm looking at a cross section. So look at the unit sphere equation. This is a unit sphere. Well, yeah, I'll write that down. That's our unit sphere, right? Right? But I'm using U for X and V for Y. And I'm saying that V is 0 when I'm looking at this, right? So in this right here has the equation U squared plus Z squared is 1, right? That's the equation of my circle. And then the equation of my cone, right? This cone equation right here, I looked at that as being square root of U squared plus V squared, but V is 0, right? So this just becomes what? U. So this is basically Z equals U is that line right there. And so you're trying to figure out where these hit each other. So just set this equal to this. So everywhere you see a Z, replace it with U. So I come to this equation, replace Z with U, we get U squared plus U squared is 1. So 2U squared is 1. So U squared is a half. And then that means that U is equal to 1 over root 2, which means that U is root 2 over 2. Oh, root 2 over 2, right? And Z and U are identical. So whatever U is, Z is. But I just wanted to know what U was, right? So that gives me my restriction on R, root 2 over 2. Okay. You all right with that? I know you're not all right with it, but are you okay to keep going? I've got this. I've decided to go to polar. Here's my polar conversion. And now I continue. So this now becomes, can I erase this? Yes? Okay, so my integral becomes root 2. Now I can put some limits of integration on here. Let's go theta on the outside. So 0, 2 pi. Let's go 0 to root 2 over 2. And now the messy part. We have, this is going to be, what? R cosine theta. This is going to be R sine theta. This is going to be R squared, right? But then just R. So U squared plus V squared should be R squared because of our conversion, but then we're taking the square root of it. So R. And then R because we went to polar. And then D, R d theta. And I think that's all within reason to be able to do this, because we're going to get r to the fourth power, right? Yes? So root 2 over 2 here, r to the fourth power dr, times, I'm going to split it because r and theta are separated, 0 to 2 pi sine theta cosine theta d theta. If we do that, we should get it. All right? Now, I'm going to have the computer do the work for me, if that's all right with you. I think I'll have it do it all at one time here. Let's see here. 0 to, I guess, 2 pi. 0 to square root of 2 over 2. I'm sorry, Brenda.
Oh, no, you're fine.
Okay.
Shaking my head like this.
Why? Was he doubting you?
No.
D, dr, dt. The only thing I'm missing out here is the square root of 2, right? Root 2 on the outside, 0 to 2 pi, 0 to square root of 2 over 2, r to the fourth, sine theta cosine, okay. 0. We get 0.
It's a waste of time.
All for nothing. Okay. Are we all right? Now, the next thing, okay, it's saying, well, no, it's not the area. This is not the area. This, because what we're doing is we're not doing the area, we're doing some scalar function times the area. So at each point on this surface, we are saying whatever that x, y, and z coordinate are, we're multiplying them all together, x, y, and z, and then we are multiplying that times the area of an infinitesimal patch. So think of it as density. We're calculating the density at every point. The problem is our density function's jacked up because it's x times y times z, so it's counting some things positive density and some negative density. And so that's why we're getting a total massive 0 of this. It's not a good example of a density function, but it's okay to get 0. All right, what I'd like to do now is I'd like us to, I don't want to change the surface yet, okay, to the correct problem. I want us to do this problem again with the shortcut, all right? And let's see how it changes. Okay, so the shortcut says this. This part right here can be replaced with this part, right? Okay, so let me get things set up. Let me get this out of here. Let me move this up a little bit. Let me make it a little smaller so it doesn't take up so much space. Okay, and now what we're doing is we're using the fact that z equals some function of x and y, which is the square root of x squared plus y squared, right? So we have this special case where our surface right here, not the frickin' sphere, okay? That surface right there is just that part of the cone, all right? Now, when I do this, I'm going to have to do the double integral over s of f of x, y, z ds, but because I am going to use my shortcut, this should just be double integral over d. What is my function x, y, z going to be? So what is it up there? X times y times z, right? Okay, so it's x times y times z, but z has to be rewritten as a function of x and y. So instead of writing z here, I'm going to put what? Square root of x squared plus y squared. Okay, so this part right here is the x times y times z, right? And now this part, the ds, is this right here, but I'm going to use this instead. Okay? So this is going to be times the square root of 1 plus, what is the partial of f with respect to x? So maybe we should do that on the side. What's the partial of f with respect to x? We kind of did that a second ago, didn't we? So we'll have it 2, but the half will kill it off. So this should just be x over the square root of x squared plus y squared. Because we did that with u and v, didn't we? And then the partial of f with respect to y would be y over square root of x squared plus y squared, right? And then when I put those in there, when I square each one of these, right, and put them into the formula, right, square them and add them, what happens when I square these and add them? If I square that and add it to this square, I get 1 again, don't I?
Yeah.
So because we've done that, I'm just going to put 1 here. And then we have dA. So this is all kind of making sense?
Yeah.
So we wind up getting root 2 double integral over d of xy root x squared plus y squared dA. Right? And that's the exact same integral we had before, isn't it? Except we had uv, didn't we? We had root 2 uv square root of u squared plus v squared, right, dA. And then when we looked at u and v, we said we had to go to polar.
Yeah.
So here we're going to have to go to polar. X is going to become r cosine theta, y is going to become r sine theta. Same restrictions, same integral, same answer. Okay? So this shortcut actually did not help us. It's pretty much the same thing, except we never had to calculate the partials and cross them, right? That never happened. So it saved us that work. So I'm just going to put here, this is equal to 0 because of what we've already done. Now, would you like to do this problem the correct way? Like answer what was being asked? I know you don't want to, but let's do it. Okay, so now our surface, S, is the part of the unit sphere that is above this cone. So our unit sphere, our cone, the part that's above it, and so we're talking about this piece right here. That's S.
It's part of the unit circle above the cone.
It's the part of the unit sphere that is above the cone. Above the cone means inside the cone.
Okay.
Because look, if you were a point right here, you would be below the surface of the cone. If you were inside the cone, then you would be above the cone. Right?
Right.
Everyone got that? Okay, now we need to come up with a way of drawing that. So how do we draw S? Well, it lies on the unit sphere, so why don't we use the thing that we learned at the beginning of class, which would be sine u cosine v sine u sine v cosine u. That's the unit sphere, right? Because I have ones in front of everything. That's unit sphere, but what are our restrictions on u and v? This is the part that's, I guess you got to think a little bit about. U was like the phi, and v's like the theta. So how are you going to draw me just this portion right here? What's your phi restriction going to be? 0 to what? Pi over 4. And the way you would know that is going back and doing what we did a little while ago, where we said the cone cuts through like this. And we determined that whatever this side is, right? Call it whatever, x. That this is also the same, right? These two are the same. So since these two sides are the same, it's 45, 45, 90. So since we know that, we know phi is 45, right? So phi is like the u, so 0 to pi over 4. And now V is the spinning around part, right? And that's going to be 0 to 2 pi. There is no shortcut here. There is no shortcut here. Well, we could do that as a shortcut. We could. I'm not sure we want to, though. We have to be able to define this region as a function of x and y, which would require us taking the sphere equation, solving for z, but then the domain on the ground, we'd have to switch to polar at the end. I think it'd be harder to do it that way. Here our limits of integration are constants. All right. Time to plug everything in. Oh, wait, hold on. We need a magnitude of a cross, don't we? Magnitude of the cross product of that? We did that earlier in class, didn't we? Can somebody go back, please help me? What was, I know we did the magnitude of R cross V. I know we did that magnitude when I was trying, remember I tried to prove to you the surface area, right? And what did we get when we did that earlier today? Didn't we get R squared sine of U? Who has the notes where I did? We're trying to prove that the area was 4 pi R squared, right? Yeah. And at the end of that, we got that this piece right here was R squared sine U. But we don't have R here. R is 1, right? So without doing the work, trusting that you could take the partial of that with respect to U, partial with respect to V, cross product, magnitude, at the end of it all, you get sine U, okay? Can I trust that you would do that? Okay, so the surface integral of f of x, y, z ds with respect to surface area should be the double integral over d of now our scalar function x, y, z. But what's x for us? X is not x. X is sine u cosine v. So this is sine u cosine v, that's x, times y, which is sine u sine v, times z, which is cosine u. You with me? That's just that. And then the next part is the magnitude of the cross product of the partials, which is sine u, right? And all of this will be with respect to dA, okay? And we know our restrictions here, don't we? For D, our restrictions are right here. And because they are both between two constants, it doesn't matter which order we set this up in. So this will become, let's do 0 to 2 pi first. Then we'll go 0 to pi over 4. And now, sine cubed u. Sine cubed u cosine u. I'm going to put the u's, sine u, sine u, sine u, cosine u. I'll put all the sine and cosine, all the u stuff together. And then in terms of v, I have sine v, cosine v. And then d, which one's my inner one? du, and then dv. Now, could we split these up into two integrals and put multiplication between them? Yes, because the u's are all grouped together, v's are together. Could we integrate this one pretty easily? Yeah, basic u substitution. U is sine of u. Well, we wouldn't want to use u. We'd have to use something other than u. Like w equals sine of u. So we could do that one pretty easy, and this one's just as easy. So these are all doable, right? Okay. I'll get you the numerical answer. So we don't have that anymore. 0 to 2 pi, and then pi over 4. And then this one, this is going to be kind of messy. We have sine of u cubed times cosine of u, and then times sine of v cosine of v du dv. I think we're good there. Oops. We get 0 again. Now look, this is just kind of a coincidence, all right? But it does have a lot to do with the symmetry of what's going on here. Because your function here, x times y times z, right, x, y, z, is, again, if we look at that as like a density function, if you look at that top cap that we had, as you move around points here, when you're in the first octant, right, those things, the density there is going to cancel out with the density in which octant? The third, because one will be positive. No, those will both be positive, because the x, y, and z coordinates will be positive in all of them, right? So the first octant and second octant's densities, right, are going to be opposite in sign. And so you're going to get the mass in the first octant is going to cancel with the second. And then the mass in the third octant is going to cancel with the fourth octant. Does that make sense? And the exact same thing happens on the cone, because the cone is also symmetric like that top cap. Does that? Yeah, okay. So if we change the function in here to something better, then we would have a non-zero answer, all right? Pardon me? Yeah, we could move the whole thing to the first quadrant. So what if we do, like, from 0 to 2 pi, just go from 0 to pi over 2, right? Let me do that because it's easy to do, right? Then we would get something other than 0. 1/32, okay? What if we go from 0 to pi? That should cover the first and second octants, right? 0, right? If we go, what if we went from pi over 2 to pi? Negative 1/32, right? So you see what's happening here? It's just the symmetry of the problem. That's why we're getting 0 in both answers. All right. We just had 35 more minutes to go. You know, I should have scrolled down. Freaking idiot. I should have scrolled down. There it is. There's the surface. See, I moved those down because I want you to read the problem and come up with the correct surface without messing it up like me. Okay, some applications, bless you, some applications of these surface integrals. So mass, this is what I talked about when I was trying to explain it. If this function here is a density function, and you're going to be integrating the density function over the surface S with respect to surface area, then that's going to give you the mass of the object. Then we have formulas for finding the center of mass, right? That's just some applications. Now, the special case, we kind of got ahead of ourselves here, but the special case of this is just, again, showing you that that piece right there comes from here. And then all you're going to do is you're going to just rewrite this scalar function. You're going to let your x's be x's, y be y's, but your z gets replaced with whatever the surface is, whatever the function is. Okay, let's find the double integral of the scalar function x over the surface S with respect to surface area, where S is shown below, the entire surface. So we better look at it, right? I better not pay attention to myself here. There it is. So we want to find the surface integral over S of x ds, right? That's what we want. Where S is this entire surface. And please take note that the entire surface means that we need to look at all sides, back side, right, everything. So we actually have 3 surfaces, don't we? So to do this, I'm going to have to rewrite this as being the surface integral over S1 of x ds plus the surface integral over S2 of x ds plus the surface integral over S3 of x ds. Right? So I'm going to break up S into 3 separate surfaces and then add them all up together. Now, what you call S1, S2, and S3 is totally up to you. So where do you want to start?
Let's start with the easiest one.
X equals 0?
Yeah.
That backside?
Yeah.
Okay. So if we're going to do that backside, that S1, we write that using a vector function. Is it a unit circle on that backside? How can we tell? Look at the green one. Isn't the green one a cylinder of radius 1?
Yeah.
So that means that backside is a disk of radius 1. So to draw a disk of radius 1, I'm going to use v cosine u. X is 0. Sorry. X is 0. V cosine u, v sine u. U between 0 and 2 pi, v between 0 and 1. So do you see, had we not gone over this first, just jumping right into it and just starting to throw up the parametrics would be a little bit weird to just start throwing them up there? So the book doesn't go through any review of how to draw these. That's why I took some time earlier to do it. Okay, that's S1. We need S2 and S3. Do you want to finish off S1 first? And then go to S2? Let's do that? Okay, let's finish off S1. So for S1, I'm going to need to do, I'm trying to do this. Now, we're going to get lucky here. Do y'all see how we're going to get lucky? X is 0, right? X is 0 here. So I could go through and I could have sat here and done the partials, right? Crossed them, did all that magnitude and put this formula together. But then when I got back to this, I would say to myself, wait a minute, I'm going to replace that with what? 0. Because we are 0 there, right? So this is the double integral of S of 0 ds, and that is 0. So we got lucky there. Didn't have to do any computations. Let's move on to S2. Which one do you want for S2? You want this green part, cylinder part? Okay. So let's let the green part be our cylinder part. Let's do S2 there. So I'll erase this. So for S2, we have R2 of UV, which will be, okay. So you got to pay attention to what, which planes we're in here. We're drawing circles, right? Like in the YZ plane. So it's our Y and our Z that need to be sine and cosine. They're unit circles. So cosine U or V, it doesn't matter. Cosine U, sine U, that okay? And what's our X component function going to be? V. Our U will go between 0 and 2 pi, and our V goes between 0 and, yeah, so we're going for the X, right? The X coordinate, right? Which means we have to take the plane equation, which is the one in blue, solve it for X, which it already is. So it's 1 minus Z, but what's Z for us? Sine U. All right, so that's our second one, our second surface. And now we need to go and try and set up this one. unfortunately for us, x is no longer 0 here, right? X is actually going to be replaced with what? V, right? And then the ds part, we need to go take the partials, cross magnitude. We got to do all that now, all right? So I'm working within this framework. This is going to get a little weird because normally here's where I would write RU, right? Like that. But I'm working with the second R, not the first one. So do you want me to put like R script subscript 1U? Or sorry, not 1, 2U? Or do you care? Can I just write this and everyone understands we're working with that?
Yeah.
Okay, so I'll just leave it like that. So what is the partial of R with respect to U? 0. Negative sine U, cosine U. Okay, partial of R with respect to V. 1, 0, 0. Nice. Agree? Okay, cross those up. Zero. Just cosine U. Sine U. Oh, we're about to get lucky.
Oh,
Right?
one.
It's 1.
It's one.
Right? Magnitude of each of those things squared, added together, right?
What extreme luck?
Yeah, we got lucky here. Okay, so now, coming back to this, right? Coming back to this. This is now going to be double integral over the domain D, which are restrictions on U and V. That's this stuff. And then X, which we said was V, times the magnitude of the cross product of the partials, which we said was 1, dA. And I don't mind that at all. Integral, let's go 0 to 2 pi, 0 to 1 minus sine of U. Now, do I get to choose the order on these?
No.
I do not, because this is not between two constants. I'm integrating V, right? With respect to what first? V first, and then U. So this is the first time today that we've actually had limits of integration that are not constants, right? So let's go ahead and evaluate this. Okay, I'm going to take the antiderivative of V with respect to V. That's half V squared. I'm evaluating that from V equals 0 to V equals 1 minus sine of U. After I'm done there, I'll integrate that with respect to U. I'm going to go ahead and pull the half out because I just don't even feel like dealing with it. I'm going to plug this into here and square it and then plug 0 in. So the 0 is not going to do anything, right? When I plug that in and square it, I should get 1 minus 2 sine U plus sine squared U. So that's this into here squared. The half has already come out. And I need to integrate that with respect to U. Half antiderivative is what? U plus 2 cosine U. And then for sine squared, you'd probably want to do like a half angle or power reducing, right? For this, you probably want to turn that into 1/2 1 minus cosine 2U. If that's what you want to do here. And then integrate this. So when we integrate that, we should get minus half of u, or not minus, plus half u, and then minus sine, no, 1/4. 1/4 sine 2u. Let's just double check this because my brain had turned off a little while ago. Okay, so 0 to 2 pi. Let's see. Derivative of that is going to be just 1/2, and that would give us this piece. And then derivative of this would give us cosine of 2u, right, times 2. And that 2 would hit, so that should get it. And now 0 to 2 pi. So 1/2. Replace that with 2 pi, we got 2 pi. Plus, what's cosine of 2 pi? 1 times 2 is 2. All right, plus, I guess I could have done that earlier, but that's just going to be pi, right? 2 pi into here. And then sine of 4 pi is 0, so there's nothing from that one. Minus, now when we plug in, let's see, 1/2. Do we get zeros the whole way? No, we do not. 0 here, but cosine of 0 is 1, so times 2, so we get 2. 0 here, 0 there, so I'm going to check my answer on the computer here. Pi plus 1, we have minus 1 plus half pi. 3 pi over 2. 3/2 pi. I'm going to check that. We're not done. This is just the second surface, yeah.
Yep.
But I'm just going to check it. Okay, so it went from 0 to 2 pi, right? Then it went from 0 to 1 minus sine of u. And then this was just v, and then it was dv du. 3 pi over 2. All right? Okay, so far the surface integral is 0 plus 3 pi over 2, right? Last surface. So on your final, what I'm going to do is I'm going to give you a surface that's like one of those 20-sided die that you get from like Dungeons and Dragons or whatever that is, right? You have to find the surfaces for each one. No? All right, I've forgotten where I am here. What is our, okay, so our last surface. So I want you to take a look at this last surface. This last surface here. Can you find the parametric for that? Yeah? All right. It's the blue one we're working on now, right? I'm looking at it from the top. It's not something I want to do. Okay, so what is it for the third surface? That's R3 of UV. So this is basically that disk equation, right? The disk formula. It's just that this time the x is going to be changed. So it was, did I use V cosine U?
Yes.
V cosine U, V sine U, U. Yep, so this one is going to be the x, but x has to be 1 minus whatever the z is V sine U. U is going to go between 0 and 2 pi. And v is going to go between 0 and 1. These partials are not going to be fun, and crossing them is not going to be fun, and magnitude's not going to be fun. But who said this was supposed to be fun? All right, so what is the partial of r with respect to u? So 0, right? And then minus v stays, derivative of sine of u is cosine u, so minus v cosine u. Partial of this with respect to u, minus v sine u. And then partial of this with respect to u, v cosine